we can solve Laplace condition of t to the power n with the help of the definition of Laplace transform. So this condition we can solve with another method, that is integration of by parts. So first I will take condition of Laplace transform, that is t to the power n. So solution, so this is a given function and that is f of t, that is t to the power n, and with the help of the definition we can solve this one. We know that the definition of Laplace transform. So definition is Laplace transform of f of t, and that is integration, limit values are 0 to infinity e to the power minus st f of t and dt. And just substitute here f of t is given, that is a time domain function or tool or frequency time domain function t to the power n, and therefore Laplace transform of t to the power n is equal to integration 0 to infinity e to the power minus st, and f of t is given t to the power n and dt. And this one we can solve by integration by parts method, and this is our u and this is v, because we have to use isolate and we are already familiar with isolate. So when you take the integration in with a product form, and we have to use the isolate condition. So u is t to the power n and v is a exponential function of e to the power minus st. So this one solved by using integration of integration by parts. So and we know that integration by parts method, when products are integration products, and that can be written, and this is a general condition how to solve when the variables are in the product and we have to use the integration. So first term keep as it is and integrate, second term v and minus an integration of integration v and differentiation of first term u. So u prime is nothing but differentiation of u term and integration v term. So apply this condition for the Laplace transform of t to the power n. Therefore Laplace transform of t to the power n is equal to, so apply this condition by parts condition, u is t to the power n and v is e to the power st. So first term keep as it is, that is t to the power n, and integration of v, integration of, it means integration limit values are 0 to infinity e to the power minus st with respect to dt, and minus integration of integration, and that is 0 to infinity, 0 to infinity, and v value is e to the power minus st, and u prime nothing but differentiation of t to the power n, and we know that the differentiation of t is a variable and n is some constant value. So we have seen some basic condition of integration or differentiation when x to the power n is there. So we apply n into t to the power t minus 1 with respect to dt, and this is the differentiation of t to the power n. So t to the power n is as it is, and integration of e to the power st, it means, so integration of e to the exponential function of x dx, we are already familiar, this is the basic condition. So So this one can be written e to the power x and coefficient of x is 1, and apply the limit. If limit value is there, apply limit values. So use this condition for e to the power minus st, because t is our variable, so only we have to integrate t only, and this one is e to the power minus st and minus s, because coefficient of s is minus s is comes in denominator, and apply the basic condition, and limit values are 0 to infinity. Again an integration, first we have to solve the inner integration term and keep this integrate term as it is, and so integration of e to the power st minus st is nothing but e to the power minus st and minus s, and differentiation of n into t to the power n minus 1 and dt. So now look at this condition. So t is our variable and limits values are given. Lower limit value is 0 and upper limit value is infinity. First we have to apply upper limit minus lower limit value, and this condition nothing but, just observe here, t as a infinity, it means substitute t as a infinity, it means e to the power minus infinity, and e to the power, so just substitute upper limit t as our infinity value, so it nothing but exponential of minus infinity, and exponential of minus infinity can be written 1 over e to the power infinity, and 1 over e to the power infinity value is nothing but 0. So in previous video we discussed of exponential of infinity values. So it's nothing but first value is upper limit value is 0 and minus lower limit value is 0. So t is variable, so substitute t is 0 is nothing but whole thing is 0. Now and simplify it, minus of minus is plus, integration 0 to infinity, and e to the power minus st and minus s and n into t to the power n minus 1 dt, and simplify it again. So I will take n and s as a just stated as a constant, take outside, integration of 0 to infinity e to the power minus st and t to the power n minus 1 dt. So this is one of the condition of Laplace transform of t raised to power n. This condition can be written as our definition of Laplace transform, and that is n over s, and this is looking like integration of 0 to integration of e to the power st t to the power n minus 1, and this is looking like the definition of Laplace transform. So we can write in the form of Laplace, and that is Laplace transform of and t as n minus 1. So Laplace transform of minus 1 is, and this is the general condition of Laplace transform. So this one and another important condition. So with the help of condition 1, and we have to solve t to the power Laplace transform of t to the power t n minus 1. So just substitute n as a n minus 1 in equation 1, and definitely we will get t to the power n minus 1. Similarly, so from 1 Laplace transform of, so we are going to find out the Laplace transform of t to the power n minus 1. So here n is n minus 1, just substitute this n as a n minus 1 in condition 1, and definitely we will get t to the power n minus 1. So substitute t as n minus 1, that is t to the power n minus 1 in condition 1, and that is n as n minus 1 and s is as it is, and this one integration again Laplace transform of t to the power tn minus 2. And also we can find out the Laplace transform of t to the power n minus 2 with the help of the condition 1. Also we can find Laplace transform of, just substitute t as n minus 2. So n minus 2 and n as, because we are going to find out the t to the power n minus 2. So n as n minus 2 over s and Laplace transform of n minus, n is n minus 2, substitute. So n minus 2 minus 1, n minus 3. So we can find out the again Laplace transform of t to the power n minus 3 with the help of the condition, and it goes continuously. So it means n value is decreased to the 2, 1 and up to the 0, because n value is some positive integer, and here reducing n values is reducing as n minus 1, n minus 2 up to initial condition, it means t to the power t naught. So also Laplace transform of n value is 2 t square, and substitute here t as n as 2 and n is 2 over s, n value is 2 over s, and Laplace transform of t to the power 2 minus 1 nothing but 1, 2 minus 1 is, substitute here n is 2 and definitely n minus, it means 2 minus 1 is 1, and again and Laplace transform of t to the power 1 value is, so n value is 1, again substitute in this condition, n is 1 over s, and Laplace transform of, and t to the power n minus 1 is there in general condition, n value is 1, so t to the power 0. So by back substitution of these values, and definitely will get by back substitution of all the above values, and that is Laplace transform of t to the power n is equal to, so first initial condition is n, or general condition is n over s, and the value of t to the power n minus 1 value is nothing but n minus 1 into n minus 1 over s, and again in this condition t to the power n minus 1, again we will get t to the power n minus 2, and t to the power n minus 2 value is nothing but into n minus 2 over s, and so on, and the value of t square is nothing but 2 over s into, and Laplace transform of t to the power 1 value is nothing but 1 over s, and Laplace transform of t naught t to the power 0. So we can write this condition. So numerator terms are n into n minus 1, n minus 2, and so on to 1 over 2 into 1, and denominator values are, so s are in multiple form, so n time of s can be written s to the power n, and Laplace transform of t to the power 0, so any values of the power 0 is nothing but 1, and we are already familiar with this one. Laplace transform of 1 is nothing but n minus 1, n minus 2, so on to and this is s to the power n, and the value of Laplace transform of constant value is nothing but 1 over s. So in previous video we have seen the constant values of Laplace transform, and this can be written, and look at this condition, and this is nothing but the condition of n factorial. So when n values is reduced to up to the 0, it means that is a condition of n factorial, n minus 1, n minus 2 up to 1. So that condition can be written Laplace transform of t to the power n is equal to, and this can be written n factorial and s to the power n into 1 over s. Therefore, Laplace transform of n factorial, and powers are same, it means bases are same, and powers will be at n plus 1, and this is the solution of any Laplace transform of variable t to the power n, and n must be n where n must be positive integer. In particular, if you see in particular cases, how to apply the condition. In particular, suppose we want to find out the Laplace transform of t square or t cube. Find the Laplace transform of t cube. Just apply the condition of t to the power n, and definitely you will get the answer. So that can be written 3 factorial over n value is s to the power 3 plus 1, it means 6 over s to the power 4. And similarly, when the value of t square, and definitely we get the Laplace transform of t to the power square, it means 2 factorial and s 2 plus 1, it means 2 over s cube. So on, we can see some many examples on t to the power n, and apply the n factor over s to the power n minus 1, and definitely we will get the solution, or yes, we get the solution. And in next video we will see some more examples on Laplace frequency or Laplace tools or signals. Thank you.